Exploration of cellular-based IoT technology. So this research started several years ago, and the purpose of this research is I helped Rapid7 spin up their IoT pen test offering. Currently, I work as a principal security researcher focused on IoT, and they spun that up, I eventually become the researcher. And the focus was, hey, we're starting to encounter more IoT technology that has cellular capability. How do we interact with it? We really can't legally sniff cellular communications to see what that end looks like. So we're used to like sniffing Ethernet coming out of a device or Wi-Fi or Bluetooth or any of the other protocols. But there are some legal issues unless you want to get into Faraday cages and properly doing it. The question is, how do we think about or how do we test IoT devices and dig into this technology without violating the law? And that's what we're going to talk about today. This spun out further from research I did a number of years ago with interchip communication analysis. The concept of most IoT devices have multiple processors on board. A cellular modem is just another form of CPU processor. Bluetooth, another processor. Zigbee is another processor. All of those communicate with something that usually functions as a primary CPU. So why not just start looking at all the communications flowing from the primary CPU to the device? Now we can start looking at things that, one, are rarely ever encrypted. So I don't have to look at encryption, and we can start analyzing these things for how they work, how the end-to-end security works on this technology. And this is how we spun off on this. So as I mentioned, my name is Deral Heiland, Principal Security Researcher at Rapid7. I've been there for over 11 years. I've been doing the research for close to 8 or 9. Before that, I worked as a pen tester for over a decade, run part of a pen test team, did all that type of stuff. In this list here, you see all the different areas I've done research in over the years. I've published crap load of CVs, somewhere above 55 CVs. Again, not all those CVs are like cool CVs. Some of them are just freaking stupid CVs, but there is some cool ones in there also. So let's go ahead and start. So this research project I've also done with a co-researcher, or Carlotta Bidner. She's a good friend of mine. She used to work at Rapid7. Now she works at Thermo Fisher as a product tester. And we've been working on this research project, and we have really cooler stuff coming out after this that we're publishing later in this year. So keep an eye on what we're doing. Hopefully we'll get our talk accepted at Black Hat or DEF CON. If not, we'll do it somewhere else. So when we start thinking about cellular devices in IoT, there's two different types of cellular modules that exist in these devices. One's NB-IoT, the other one's LTE-M, M1, M2. And the NB-IoT, there's two bases, NB1, NB2. And if you look at this, you can actually see the speeds. It's half duplex, lower speeds on this technology. Often you'll see these implemented in devices that are only passing telemetry data out, not pictures, not images, not voice, nothing like that. It's usually a lower bandwidth telemetry data that's pulsed out as needed on these particular devices. And again, it's half duplex. On the other side of this, you'll see LTE-M devices. This is much higher bandwidth. You can see it's 1 megabits, 4 megabits, download speeds, it's full duplex. And you'll see this in devices that have to pass way more data out there. You may see these built into cars. Car telemetry data is probably way much bigger bandwidth, and maybe images, graphics, all kinds of stuff that gets sent out from these devices. So you'll often see these type of devices actually used from a cellular module standpoint on IoT technology. Now, these standards all come out of the 3GPP organization, and there's been various other releases that have came out, the 15, 16, 17. There may even be more since the last time I put this together. And this covers some interesting things like improved access control, small cell support. That's the idea of being able to spin up a small cell tower, small cell structure that will handle lots of devices. Let's say you have an environment where you're going to have hundreds or maybe thousands of devices that can't actually be handled in a normal cellular environment or could overwhelm it. You can put microcells up or small cells and be able to have these devices actually function that way. So during this, we're talking about, this is a lot of hardware hacking. So that's how we kind of interact, because I mentioned interchip communication analysis, capturing data flowing from CPUs to the actual devices, possibly even man in the middle of that communication, controlling the devices. So some hardware hacking. So I thought I'd throw a couple interesting techniques in here. And one of them deals with how do we identify interesting connection points. Typically, there's three main connection points on cellular modules that are interesting. Two of them are UART. One's a debug UART. One is a command and data UART that goes to the CPU. The debug UART you can actually attach to, watch the device boot up. Some of these have full operating systems on them. You can actually see them boot up, and some of them actually have logons. You can log onto these devices if you know the password. The other one happens to be USB. So when these devices are put together, how do you, as a researcher or attacker, find out where the connections are? Because we're dealing with modules that are utilize land grid arrays or broad grid arrays. That means everything's underneath the chip. So you can't see where it's at. And it may go through sublayers, it may go through the back layer of the device, maybe on the top layer. How do we figure out where to start looking? Because there's a lot of connection points on the device. So in this particular process, we kind of take both sides of the board and we photograph it. And then we do a 50% see-through. So now we can instantly see the components in reference to each other on each side of the chip. Now, this will work on any modular type device and potentially even a ball grid array device if you want to do it to it. And then what we do there is we find the data sheets, we get the land grid layout, and we transpose it over top of it. And by doing this, then we can actually trace out where cool things are, like UART connections, the serial connections we're interested in, and the USB. So now if we know we're going to look for something, we're not going to look on the other side of the chip. We can start looking in that general direction or that general direction on the other side of the chip and figure out where we can find tap points. This comes in really handy. It's easy to do. I typically do this up in PowerPoint, but there's other tools you can actually do this stuff too. Photograph them, transpose them over each other, do 50% overlaid chip information from the data sheets on there. You can quickly start identifying where the things you want to find are located on the board, potentially tap into those. Also, while I was doing this, I started thinking, well, what if we didn't find anything? So what if we start looking and we didn't see anything on the surface of the board? Let's suppose they put it all in a sublayer on the board. What could we do? Now, this doesn't apply to everything, but it applies to a number of cellular modules, especially the smaller ones, the NB-IoT ones. So here is the actual underside of one in a data sheet, a schematic of that layout. And if we look at that, we see a lot of things around the outer edge of this. That's typically where all the cool stuff are. So I'm like, okay, the cool stuff's pretty close. How will we get access to it? Well, if you turn on the edge under magnification, you can actually see the land grid arrays underneath there. So I thought, I wonder if this is possible. Let's put together some acupuncture needles. So we built acupuncture needles, and we're actually able to successfully insert those up underneath the body of the chip and gain access to critical communication lines on the device. And it works very effectively on these smaller modules. The bigger modules, you have a bigger gap between the edge and where the land grid array starts, so it doesn't necessarily work well. But it really comes down to how the board was put together. If they actually put larger lead or connections in there where there's a bigger gap, then you can get to those also. This one was actually 0.2 millimeters from the edge, pretty close. The other ones, the larger ones, like the one we showed in the previous picture, that one's about 3 millimeters from the edge, so it's much farther away. Still doesn't mean it can't be done, but you have to use smaller acupuncture needles, which are very flimsy and hard to force up underneath something. But the heavier acupuncture needles work pretty good. So with acupuncture needles, if you go out and say, I want to buy acupuncture needles, you cannot buy these. These are considered medical and you cannot buy them. How did I get these? Well, apparently 3D printers actually sell acupuncture needles used to clean the nozzles out. They're actually medical acupuncture needles. They just relabel them and they can resell them. And that's how you buy them. And I have like a crap load of them. They are made out of stainless, so you can't solder to them. So you're going to have to use some kind of crimped connections to make connections to these things. because being stainless, you can't connect to them with solder. And we're able to get this up, and we're able to capture data off of it and see all the serial communication from the primary CPU and capture that data unencrypted. So let's start looking at the communication types that we're going to encounter on these cellular modules. And I already mentioned this, but they fall into these categories. You have 3 different communications. You have USB, you have UART debug, and UART main. The UART main and the USB are always used for communicating 2 different things: data that's going to go out over the cellular network, and cellular module command structures. That's stuff that tell the modem to connect out using these credentials and these passwords and all that stuff. When you're looking at IoT devices on cellular on an IoT device, both of those are not going to be used. It's going to use one or the other. So if it's being used in USB, typically UART's not going to be connected. In a few rare cases, you'll have modules that are produced, secondary market or third market modules actually produced. Well, they have both of them connected, and the manufacturer will use it, and they'll tie into the one they need. In those cases there, both of them may be connected, but both of them will not be used. The device we have here, it turned out both of them were connected, but only USB was actually used in that particular case. And again, the USB on most of them is USB 2.0 standard. There's also a third standard you're going to see. It's rare. I just got a device. It turned out that it had that capability, and is known as high-speed interchip comms. So it's a completely different protocol. It's kind of like a subset of USB, but it's definitely a different protocol, and you have to use different methods to actually connect to it. So we're going to actually look at USB capture and decode. So the device we're going to use today is actually a field camera. So it's a field camera. So we've taken a field camera and we've actually put it on a breakout where we can make all of our modifications to it for testing purposes. So in this particular case, we're actually going to look at USB. So it turns out that USB is very sensitive. USB, the runs actually on the board have to follow very strict standards or it breaks. So when you're going to connect something to it, you have to follow certain standards to connect to it. In the case here, I have what's circled there is the USB as it transferred over the circuit of the board, and there's 2 resistors there. It's not uncommon to actually see USB and sometimes even UART having impedance matching resistors in line with the circuit. Turns out in this case, though, those are 0 ohm resistors, so they really mean nothing. They're just connection points on this particular device. But to be able to attach something to it, to sniff it, was a big problem I had. Most manufacturers produce a number of USB devices out there for man-in-the-middle USB. So this would go from a USB device to your laptop, and you could actually sniff data. But it's only in line. What happens if I want to sniff data in circuit? You can't really use a logic analyzer unless you're like filthy stinking rich, because it's 480 megabits per second. And most standard sniffers, unless you get into the $5,000, $10,000, $15,000 range, are not capable of doing it. So I went on a hunt to find a manufacturer that would produce a USB device that could do inter-chip communication sniffing. Took me a couple years, but I found one, Beagle. They claimed they could actually do this. Now, the other solution is you just start buying devices and trying them. That's a very expensive effort, even if they're open source technology and where you can get devices for a couple $100. My fear was, hey, how many of these different products am I going to go through and never find one that works? They claimed it would work. I bought one. This was $1,300. If you're doing testing, IoT testing type stuff for a company, I highly recommend you have one of these in your kit. The way you connect one of these things up is you can't just connect it to the circuit. You connect right to a USB circuit, you're going to cause a couple problems. You're actually going to load the circuit down. You're going to cause echoes by adding extra lines to it, so signal echoes that'll actually happen. So what we had to do was this device required you to put a 20 to 40 ohm resistors between this device and the actual USB circuit. So you can see in this picture here, I've actually soldered up to 33 ohms, about right in the middle, 33 ohm resistors. And we went ahead and attached a USB cable that actually went to our device. And that gives us the ability to potentially sniff that. Now, this video is actually from the first time I tried this. I'm like, I don't even know if this is going to freaking work. Just spent $1,300. How bad is this going to go? Let's kind of look at it. So as this video runs, I'll expand out things. But what we're going to do is we're going to connect to this thing, power up the device, start the sniffer software, and we're actually going to get to see some interesting things take place. So we just turned the device on. So now it's receiving all the USB communications. In circuit, we're sniffing it. So we go over data. I only want to see data. I don't want to see USB handshake data. We start looking at the data. Instantly, we start seeing AT commands. So we're going to dig into AT commands a little further in a minute. AT commands are actually used for sending command and control to these devices. So we can see all the settings, configurations being transferred to the USB modem in here. One of the things we also see, we'll get it up here in a second, that's actually the version of the software running on the device. And if we come down here, we see some the actual APN for the device that it's connected out to. But we also, since I said interchip communications rarely ever encrypted, what you're going to see here is all the keys, certificates, passwords that are used to actually authenticate this device out to the S3 buckets for storing all of its data. So now we have all the data. Now, if you're actually doing testing of an entire ecosystem, this gives you the ability to capture all this data, strip all the critical information, keys, passwords, certificate information, take it offline for testing their cloud services associated with that product. So it comes in really handy. And I didn't show you all the details because I don't trust none of you. So I made sure that I only got pieces of stuff. So when people take screenshots, they're like, oh, there's his keys. Oh, there's his password. There's a certificate. Let's go do evil things to Deral. And we can see the actual devices configurations being exchanged. So it comes in really handy. Now we have the ability to go, hey, I can't see who this device is talking to normally. I can't sniff the cellular comms. But interchip communication analysis and capturing of data, we're able to capture all that critical data to do further testing. And it's usually unencrypted. Have I ever seen it encrypted? Not on these type of devices. I've seen it encrypted on devices that would be routers. If it's a pure, just a router that use cellular communicate out to the internet, I've seen those often set up encryptions out to the cloud. But most IoT devices do not encrypt any interchip communications. At least I haven't encountered it yet. What's that now? There you go. Yeah, that ruined my life, man. Okay, so now let's talk about the serial aspect. We looked at the USB. Let's look at serial communications. So when we're looking at serial communications, like I said, the CPU talks to the cellular module or any other device that happens to be a communication device. This applies to a number of different things. It also applies to Bluetooth chips. So we can easily throw an FTDI device on there or a listening device and listens to both sides. Remember, this isn't like a serial console where you hook both transmit and receive up. We don't want transmit. We want receive because we got communications going in both directions from the device. We want to sniff both sides of this. So if you want to inject data into a serial communication circuit on a device, you cannot just hook to it and start injecting. It will totally ignore it. It won't work, period. You have to actually separate the connections between the CPU and that to actually inject any of your actual data. There are some exceptions to that. If devices happen to have impedance resistors in line on the serial communication, then in those cases, you can often tap in. You just got to tap into the correct side. One thing I found out with those, if you tap into the wrong side, it'll load the circuit and serial comms will quit working. But in this case, this device does not have any kind of resistors in line in the circuit, so you're able to tap into that. So how do we go about it? How do we leverage this in a number of cases? This case is simple since this device doesn't actually the serial for anything useful because it's all USB. We can just cut the lines and off a run and tap into it and do whatever we want with the actual EG91 chip. But what we like to do is to get man in the middle of the communications. We want to route all the communications off the circuit board into a breakout board. So in this case here, we trace out all the serial communication lines on the surface of the board. We actually cut the runs and we hook lines to each side of it. And we send it out to a breakout board. This breakout board gives us the ability to come in from both sides, use an on and off switch. So now we have an on and off switch in the circuit. If we need to open and close this, we're able to open and close this if we want so we can inject data. We do have some other cool stuff we did that we released a number of years ago, a tool called a Karen proxy. A Karen proxy is a serial inter-circuit communications serial proxy. So in this case here, we can set our proxy up on this and capture the data going in both directions, record it, replay it, and inject our own commands within the proxy, which is kind of cool. We're actually going to be doing that at Black Hat Arsenal. We'll actually be showing the tool. We're hoping to add a few more features before then. So it's kind of cool. So this gives us the ability to inject into the actual circuit. And as you heard me mention earlier, as you've seen in the USB display, these devices use what's known as AT commands. So if you're not familiar with AT commands, this is ancient history. If you go back to the old days of cable modem or modems, AT commands used to be used for modems. Well, AT commands have not gone away. AT commands are used quite extensively on a lot of communication devices, including cellular modules, satellite modules. Also, a lot of Wi-Fi modules will actually take AT commands if you're not familiar with it. I know like the Express-F series of chips we're most familiar with, you can literally send AT commands to that. And if you have one that's configured to act as an access point, there's an AT command you can send to it. It'll actually give you the keys, the Wi-Fi pre-shared keys configured in the device unencrypted if you send the right AT command to it. So AT commands are pretty advanced. So we're going to go ahead and look at it. There's 4 different types of AT command structures. There's what's known as a test function. A test function will actually query the command and give you the syntax of what the command should look like for the most part. You also have the read command, which will read any settings that have been made with an AT command for that particular parameter. You have the write command where you can write and make changes to the device via AT command, and then execute, where it'll actually execute functions. That's where it doesn't store anything, but it actually carries out some level of execution. So AT commands have a lot of cool capabilities. They also have a lot of custom AT commands. And a lot of the vendors will put their own syntax in the AT command, as we see here with QuickTel, Ubox, Telnet. They all have a starter in their command, and that QuickTel is like a queue in front of the commands. So if you see in the commands we're running, this is a QuickTel chip, so you can actually see the queue used in the commands for it. So there's also a cool command, and this exists on a lot of the cellular devices. It's called AT-CLAC or CLAC. This will actually, well, what it's supposed to actually do is dump all the commands. All the commands that are capable in that device, it'll give you an entire list. The truth is, that's not true. There's a lot of AT commands that may exist on a device that won't be in that device's documentation or put out by the CLAC command. But we'll show you how to get that stuff because we put together some proof of concept code to actually do that. So let's go ahead and do an AT command video here real quick. So we have the device on the right-hand side, and we're going to go ahead and turn it on. And remember, all the communications on this device is via the USB. So this thing's still functioning properly. And we can use the clack command and see it dumps all the commands on this particular device. And we'll run a couple more commands here. So I think the next command we run will actually bring back the device's serial number. So this, and I hid the serial number again. I don't trust none of you. And this one happens to be the command for your actually a subscriber number, which I blocked too because I don't want you people screwing with me. It may be the IMI. But it's a subscriber number. So here's a command we're going to run right here. This is kind of cool. This is a config command, and it'll show all these deeper dive command structures that exist on the device. And we're going to run a command specifically this. There are some functions that go during boot up, during normal boot up of a device, and we're going to check to see what this device is doing during its boot up. Will this actually, and we're actually going to test for web services. Are web services enabled on this device? It came back with a 0. That means no. You see the device powered down because these are low energy devices, so they do a cycle and then they power off. We power it back up, and we're going to do one for actually WAN link services. And now we see this device has a WAN link service running on it. Basically, the USB on this device is functioning as Ethernet over USB. Is what it's functioning as. And that's what that's telling us for WAN link services, or one of the functions that tells us that. So you can see, we can actually see a lot of commands. We can execute commands on this device. Now, while I'm executing these commands, it's still a camera. It's still functioning as a camera. It's talking to its cloud services. It's authenticated. It's moving data. It's taking pictures of you. If you notice, everything's covered with tape in the picture because I hate having pictures taken of me when I'm screwing with things. And then we get into other commands. So it turns out that, as I mentioned, that the manuals for some of these devices do not tell you all of the commands that exist. These are some of them. HTTP, MQTT. The cool ones, raw TCP, raw UDP sockets. So you have those capable commands on this, but in the manuals for this device, it says, no, we don't have those. So we created a script called AT Query. And then what we did was we took all of the manuals that we could locate, AT manuals for all the different chips for each one of the vendors. We may have missed a few, but we tried to do that. And we wrote a script that gives us the ability to run AT commands to check out a device, either dump all of its configuration settings or check to see what commands are actually working and functioning. So we're going to go ahead and run that script here. So what we're going to do is we'll fire up the device. Of course, it's not running. Start it. We're going to fire up the device. I guess we're going to look at the actual thing first. So in this command, what we need to do is we need to know what our serial connection is to the actual device over USB, which is serial to USB device. So we get that out of our device, what our FDDI look like, and we make sure it gets set into our script and at the right baud rate to actually work. And this is the command structure. So we have the ability to pick the vendor. And this time we're going to do a quick tail, and we're going to do a test function, which is going to bring back all the commands that are actually on the device and their syntax. We fire up the device. We're listening over another serial connection because we want to see it come to the ready state. That's the only command to the CPU, and the CPU doesn't care. And instantly we start dumping all of the commands. And by doing this, we identified that this particular module had all of those raw socket capabilities, HTTP functions, a bunch of other features that weren't documented in any of the manuals for this particular chip, which gives us a whole big, interesting area to potentially dive into. All of these scripts are available online in GitHub I have out there. So if you want to get them, you want to add to them, you want to generate an AT command manual list for something that's not listed there, vendors, please do it. Share it with us. It'll come in handy. We'll just add it to the whole list. So we can see a number of things work, some don't work, but it gives us the ability to see all the different commands and syntax that are actually enabled on this particular device, which is extremely useful. So then we get into injection attacks. So now that we have the ability, we know what the commands are, we know what the capabilities are, we wanted to put together a proof of concept for this particular presentation. Later this year, we have way cooler stuff coming out in this category from an attack standpoint. But this is a good proof of concept. And so let's think through it. So this is how this actual device looks. We have the primary CPU on there. We have the EG91 cellular module. USBs are intact, fully functioning on this device. We cut the runs. We route out to our FTDI on our breakout board. And we are going to look at actually the socket commands. This is a TCP socket command called ATQI open. This is used for opening sockets. ATQI close would be used for closing sockets for TCP. These are the error messages you can get back. Error message, operation successful. We actually made a full functioning TCP connection to a device in a port. The other one is 566, socket connect failed. That means it did not connect to that particular socket. So if you really think this thing through, what does this mean? This means we have the ability to actually turn this into a port scanner. So this is a quick demo of this. I've rewritten this program completely with way more functions and features and cleaner looking, but we're going to show you this because that's supposed to come out later in the year. And what we're going to do is we're going to take a quick look at the code. It's typical easy Python code. We're setting our connection up right here, make sure that we can sniff it okay. We're going to go ahead and VI QI scan down through this. There's several things that had to be set on this thing. We actually have to define the actual serial connection, the address we want to talk to, the port numbers we want to check for, and of course this list can be as big as you want to. And again, the script's been completely rewritten. And here's the AT commands. We open it, we close it, we put a timeout in there so we don't overwhelm the cellular module chip opening closing sockets on this thing. And then we go ahead and we kick it off. We got a ready command, make sure it's going to communicate fine, switch over to our program, and we run QI open or QI scan. And we quickly find out that port 21 is closed. Port 22 is open. Closed. As you can see, we can quickly identify open ports, closed ports via this. Now, the next slide, we're going to talk about what this actually means. So we only have one more slide here. So we're going to talk about what this actually means. So this device, turns out, is typically off-the-shelf technology. With off-the-shelf technology, we connect out to what's known as a public APN. Public APN will give you just internet access. Not all devices use public APNs. If you go out and you purchase a vehicle, vehicles don't always use public APNs. They use what's known as a private APN. You may get a medical device that they put on you that has cellular capability. Often that may not be on the internet. It may be through a private APN. So what's the purpose of a private APN? Purpose of the private APN is higher level security. What that means is we don't want to expose all of our functions and services on the internet for everyone to hack and attack. So we're going to drop this through either into an internal network or into a DMZ. And generally it looks like this. We connect out from the device to a private APN, and from the private APN, it's actually a VPN into an internal network. So now if you think about those devices, and you think about what we're doing here, where we quickly tapped in, it gives us the ability to leverage the physical hardware to actually gain access into a company or organization through attacks. So now we can go ahead and go, hey, I have this device, I have a car I want to hack on, I have a lot of different things that may use private APNs. Gives us the ability to go to that next level, to be able to connect in, pivot right into an internal network. Now, I can't talk about the research that's coming, but it goes way beyond what we're doing here. It's It's just cool shit. Let's just put it that way. So that's coming later this year. There'll also be a paper later this year where we target that particular aspect, where it focuses on weaponization of the IoT technology in this area. Yes, sir.
So I know there's things like Shodan, so you can look up cameras on the internet. Are there any ways to enumerate APNs?
Oh gosh, there's like they're like published online from at least the public APNs. Private APNs, I don't know. I wouldn't expect someone to publish their private APN connection services out there, but you never know. People can get stupid every day. But yeah, public APNs are out there. I mean, when I started with this device early on, one of the things I was wanting to do is actually use it to send SMS messages, you know, through this function here. The problem is the APN this connects to doesn't allow SMS messages. I tried pointing it to another public APN just to see by chance would it allow me to connect, and it wouldn't allow me to connect. But we use this, and we demoed. I did this a couple years ago where I was more comfortable in an environment to do live demos, and we actually started connecting out, dumping web pages and stuff um, through this because it has HTTP functions. So we can go out to this URL, pull this thing. We're actually able to dump web pages. And of course, it was the raw data. It wasn't graphic, but we're able to gain access to all that. You can do FTP over this, but these are all things that are actually on the internet. So the interesting thing in reference to this attack and our future attacks is the concept of trust relationships. So we know this device connects out to the cloud. It connects to the S3 bucket. Others may connect to other functions or other services. But it comes down to what is the trust relationship between this device? There's a lot of assumptions when you think about embedded technologies where there is this inherent belief of trust because it's hardware. It's a machine to machine communication. It's not human to machine communication, it's machine to machine. Historically, I found most machine to machine communications often have an inherent level of trust that is falsely given. And if you can physically control the device, and in this case, we have full freaking control over this. We can send any commands, any data, anything we want, and have the cellular module do it for us. Um, and that becomes a totally different story from an attack vector standpoint. You had another question?
Yeah, I was curious. Since it does have an HTTP server, have you looked at the feasibility of using it as a C2 channel into an organization?
Sky's the limit. If you can connect, if you can hack the device and get the control of it, like we've shown here, and it connects into an internal network through a private APN, then you can do anything you want. There's literally nothing stopping it. And so there were some attacks few years back against devices that utilize private APNs where they actually pulled the SIM card out. And because all the authentication and trust was applied to the SIM card, pull it out of the vehicle, plug it in. Now we can actually gain access to internal network. I think it was a black hat talk. But as we kind of think through these various aspects of it, how do you protect from that? One, we go eSIM, adds a little more difficulty to it. IMEI number, hey, we tie the IMEI number into authentication. Now it's tied to the cellular module. So it gets harder and harder and harder things you have to do to gain access. Our idea was, hey, how can we use all the trust and functions on the device itself, not port anything off, but just use the device to do all the dirty work for us. We just got to learn how to interact with it. And that's some of the things we're talking here. How do we interact with this device? So like I said, we have some cooler interaction coming up in the near future that we've been testing in the labs that freaking works and is like really cool. But again, the whole idea of this is the trust relationship. How much trust does the vendor on the other end, whether it's cloud services, APIs, functions, things like that, they trust this device? Now, this device goes out and authenticates into the S3 bucket and all that stuff. So then my question is, and I ain't tested it yet, I don't know, do I need to pass a token or session every time I need to make an attempt into the cloud services? And if the answer is no, that this is already built trust relationship for anything coming from that port, that cellular module is trusted, and I don't have to continue adding a certificate or key every time, then at that point, I have a chance to have an authentication into the actual cloud services, and I can leverage the device to do other testing and functioning and stuff like that. So that's the theory that we're in the process of testing right now. But again, it's all this focus around machine-to-machine trust relationships. How do we leverage the device and use the device for all the evil and stuff like that? So here is the list of stuff. So in here, there's a cellular paper we put out on this. There's interchip communication, which is a cool paper where we talk about a Karen proxy and how to actually use it. And then just general blog stuff that I have. So I'm always, all my research is public information. We're going to publish it. No matter what I'm working on, eventually gets published. So just keep an eye on that stuff, and you'll gain access to some interesting stuff as it hits the street as we work through some of this stuff. Are there any other questions? Anyone have any questions? Yes, sir.
The research that's coming out, where's that going to be posted?
No. So I won't have a paper ready. We have a talk into Black Hat. So if we get accepted, then obviously we'll be talking about it there. But we won't have a paper ready by then. I just too much on the plate. But I expect a paper on the next level of the research to come out at the end of the year. And that's whether we speak at Black Hat or not. It will be on Rapid7's site or through Rapid7. Usually the best way is, I don't have a link on there for my LinkedIn, but you can see my name. I'm like the only person with that name on the face of the earth. So if you push that on the internet, you're going to find me and only me. If you go to my LinkedIn site, I put all the papers that I've published out there because often they get lost in the scramble of things changing on corporate sites. Yes, sir.
In reference when going through your research, have you noticed any correlations of TTPs with your research and threat actors such as Salt Typhoon?
I have not. And I have to admit, when it comes to some of the threat actors, I have not delved into that area. I'm like heads down, ones and zeros on hardware stuff most of the time. Every once in a while, I lift my head up and listen to somebody talking about stuff like that. But sadly, I haven't had a chance to tie any of my research back into threat actors. I assume over the years, the stuff I've published over the years, more than likely, some of my stuff has been picked up by threat actors. I remember years ago when I was researching an attack against Xerox, where you could send a print job and kick back a root shell. I was literally being stalked by a bunch of Chinese students out of Beijing until the research dropped. So who knows what happened after that with it? So it was kind of interesting. That particular research ended up the whole Air Force base in Dayton, Ohio, changed all their printers and went to a wholly different printer because of that research. It was funny.
Just get a different vendor.
Yeah, well, I like the vendor they went to. There's some vendors that actually care. And don't get me wrong, Xerox is a good company and they care about security. So I'm not besmirching anyone and putting them down. I've worked with them dozens of times, and they're really good company. Any other questions? Yes, sir.
For like authentication on these private APNs, how do the devices come baked in with credentials for their APNs, or do you like create?
So it's an interesting question. Typically, the credentials, when the device is set up, some level of authentication is defined ahead of time, just like when you set up one of these devices with the cloud services or whatever. But typically, that comes from the CPU. Now, it can be put into the cellular module, or it can just remain in the CPU. I've worked with vendors in the past where I've tested their devices, and I'm like, hey, dude, you're like transferring all this stuff from your CPU to your cellular module, and I can just capture it all. So some vendors have actually started, in that particular one, moved all of those authentication credential data over to the actual cellular module, making it harder to sniff it. It doesn't make it harder to use it because it's still connecting out, but making it harder to actually sniff that. But that's all going to be built in. Most of the devices, anytime you get a device that has some kind of serial number or barcode, you shoot it with your mobile app and it configures it. Usually that all plays into the whole authentication, but it's tied back to that. It's usually some kind of salted hash of that actually used in it. I know the interchip communication paper that I put out, we were actually observing that, where once the device is set up, the authentication never actually changed ever. So it was never salted after that. It was fixed key based off some kind of hashing algorithm and the actual registration key on the device. So I figure the APN is going to have some of that. It's going to be something similar to that. It's going to be registered to the public AP or the private APN, and that's going to handle the transactions from the cellular module. The sad part is I haven't got my hands on a private APN device. I've been trying to, so I often will build out research projects where companies can come to me and say, hey, we'll let you have access to this, and then I'll do a full assessment of everything, help them fix everything, and then we go ahead and go public with a paper afterwards. But you can imagine how difficult it is to get companies to do that. But I'm still trying, I'm still moving in that direction, and that's my focus. I've only had one company successful, and it wasn't in this category, and that was with Domino's Pizza. Domino's Pizza literally let me into their store environment to get access to their Flex in-store order management system to do research on and publish every bit of it. So it's hard to get companies to do that. Yes, sir.
They give you free pizza. Two-part question.
No, they didn't.
On two sides of the coin, are there any vendors that are particularly good at protecting, and are there any vendors that are particularly bad? If you consider.
So I haven't come to any that are. It's not necessarily the vendor of the chip; it's the implementation. It's where the flaw usually fall. Most of these vendors do some really cool stuff on their modules themselves. Because typically, if I get a new module, the first thing I do is I strip it bare. I literally strip all the components off down to the circuit board and reverse engineer the circuit board to see, can I get access to JTAG on the surface? Can I access UART? Can I access USB on the surface? And I have yet to find a vendor that screwed that up yet. Now, I just got a new device. I actually got a telemetry dice for Honda, a new one. It's like, 2023 that I wanted to play with. I opened it up and I don't even know who I know who the vendor is, but I was shocked that the vendor's name on the cellular module, never seen one. In that particular case, that wasn't LG, a land grid array or ball grid array. It actually had leads around the outer edge. So I had access to everything without any real hardware hacking, which was kind of cool. And I haven't fired that up to see what I find yet, but that's on my bench for teardown, even if it's not fully functional. Or the reason why I bought, this is all going to go online, gosh, but the reason why I bought Honda, apparently Honda has a bigger history of not decommissioning VIN numbers in crashed vehicles. So I'm thinking this came out of a crashed vehicle, so that if they didn't decommission that VIN number on the crashed vehicle, this telemetry unit may still be cellular functional. That's what I'm hoping. Now, I will not do any connections with it. I just want to see how it works on this end. I will not, under any circumstances, use that to pivot to an internal network without actually working with a vendor together to make sure it's done correctly. Any other questions? Well, I hope you enjoyed that. Hope you got something good out of it.